Hi, wishing you all. I'm Dr. J.P. Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I wish to tell about the spontaneous and stimulated emission of radiation. So, already we have been discussed about the lasers. So, in that last session, we have seen about the lasers introduction and then what are the characteristics of the laser. So, laser has monochromaticity, high intensity, coherent, and divergence. So these are all the characteristics of the lasers. So today we are going to uh, discuss about the spontaneous and stimulated emissions. So in this session, we are going to cover these topics, that is introduction about this topic, that is spontaneous and stimulated emission of radiation, and then we are going to see about the stimulated absorption of radiation, spontaneous emission of radiation, spontaneous emission of radiation, stimulated emission of radiation, and then finally we are going to see the distinction between the spontaneous and stimulated emission of radiation. So these are the topics we are going to see in this session. So first of all, let's go for the introduction. So when the radiation is nothing but photons. So when the incident radiation interacts with the atoms in the energy levels, then their distinct process can be takes place. So that when the incident radiation interacts with the atoms interacts with the atoms in the energy levels, then there happens different processes. So that different processes are stimulated absorption of radiation, spontaneous emission of radiation, and stimulated emission of radiation. So these are all the three processes which are happening when the incident radiation or incident photon interacts with the atoms in the energy levels. So suppose that we know that the energy levels, so the different energy levels, when the incident photon interacts with the energy level which is even, then what happens? Then what happens? So when the incident photon interacts with the atom which is in any of the energy level, so then the process takes place. Those processes are stimulated absorption of radiation, spontaneous emission of radiation, stimulated emission of radiation. So first we see that stimulated absorption of radiation. So in this stimulated absorption of radiation, let's consider two energy levels of energies. So we are taking two energy levels, that is E1 and E2. E1 and E2. So such that E1 is greater than E2. So that is energy level here, E1 is greater than E2 for an atom. So let N1 and N2 are the number of atoms per unit volume in the energy levels E1 and E2. So here N1 and N2 are the number of atoms per unit volume. So we'll take the energy level E1 and E2. We are taking energy levels E1 and E2. So in this energy level, so let it is the E1 is the ground state energy level and E2 is the excited state energy. So here in the ground state, the number of atoms per unit volume is N1. In the ground state, that is number of N1 is number of atoms per unit volume in the energy state or energy level E1. So likewise, N2 is number of atoms per unit volume in the energy level E2. So here number of atoms in the E1 energy level is N1. Likewise, in N2, N2 is the number of atoms per unit volume in the energy level A2. So here you can see that stimulated absorption of radiation. So in this stimulated absorption of radiation, the incident radiation consists of photons which have the energy equal to the energy difference between two energy levels. Excuse me. The incident radiation consists of photons of energy equal to the energy difference between A1 and A2. So the number of photons per unit volume of incident radiation is known as radiation density, that is, which is related to the incident. So the number of photons per unit volume of incident radiation is known as incident radiation density. Suppose there is two energy levels E1 and E2. So here the incident photon h nu, incident photon is h nu. So here these photons of energy is equal to the energy difference between the two energy levels. So that here this h nu, photons of energy h nu is equals to E2 minus E1, energy difference between the two energy levels. So the number of photons per unit volume of incident radiation is known as incident radiation density, which is denoted with rho v. The incident photon stimulates the atom in the lower energy level, that is E1, to absorbs its energy. So when the incident photon gets interacted with the atom of lower energy state, then it absorbs photons energy. After absorbing the photons energy, the atom transits to energy level E2. So this process of exciting the atom to higher energy level by absorbing the stimulating incident photon is known as stimulated absorption of radiation. Stimulated absorption of radiation. That is here in this diagram you can clearly understand. So here the lower energy state is E1 and excited state energy is E2. So the number of atoms per unit volume in the ground state, in the lower energy state, is N1, is N1. Likewise, the number of atoms per unit volume in the energy level E2 is N2. So now the incident photon is going to interact with the lower energy atom. Lower energy atom. So this is the atom which is at lower energy state. So this photon is going to hit the atom. So when this photon of energy h nu hits the atom which is at a lower energy state, then this atom, ground state atom, gains energy from the photon and get excited to the higher energy level. So after interacting of photon, incident photon, this ground state atom transits to higher energy state. So that's why here in this second diagram, so the energy here E1 is empty, then the electron transits to the higher energy state. Now this atom is at the energy level E2. Okay, so when the incident photon interacts with the ground state or lower energy state atom, this atom gains energy from the photon, then it transits to higher energy state is called the stimulated absorption of radiation. So this is depends upon the number of photons per unit volume of incident radiation. Okay, so this uh, number of photons per unit volume of incident radiation is known as incident radiation density, rho v. So the number of stimulated absorption depend upon the number of atoms per unit volume n1 in E1 and the number of photons per unit volume of incident radiation. That is incident radiation density, rho v. So this stimulated absorption of radiation depends upon the two things. One is number of atoms per unit volume in the even state, and also the number of photons incident on the atom or incident on the even energy state. Okay, so the number of stimulated absorption depends upon number of atoms per unit volume n1 in E1 and then number of photons per unit volume of incident radiation. So it also depends upon the rho v. So now we will calculate that number of stimulated absorption is proportional to N1. So N1 is nothing but number of atoms present in the E1 energy state. So the number of stimulated absorption is also proportional to rho V. So it is proportional to N1 rho V. So it is equal to N1 B12 rho V. So where B12 is the Einstein's coefficient of stimulated absorption of radiation. So if this excited atom transits to lower energy level even, then it emits radiation. So when it emits the radiation, there again two process takes place. So the emitted radiation are of two types. One is a spontaneous emission of radiation and the other one is stimulated emission of radiation. So the stimulated absorption of radiation is nothing but when the incident photon interacts with the lower energy state atom, then the, the atom gains energy from the photon and transits to excited state, transits to higher energy state. So this process is called as stimulated absorption of radiation because the lower energy state atom get stimulated by this incident photon. By this incident photon, this lower energy state atom get exciting, so stimulating, so that after stimulation, what happening? It transits to higher energy state. That's why we are saying stimulated absorption of radiation. So the lower energy state atom absorbing some radiation from the incident photon and stimulated then transits to higher energy state. So that's why in the second diagram, so this is the lower energy level E1 and the E2 is the upper energy level. So in this lower energy level, atom is here So photon is interacting with this atom, so it transits to higher energy state. So the energy is equals to the energy difference between the two energy levels. So the stimulated absorption of radiation depends upon the number of atoms per unit volume in the lower energy state and also instant radiation density. That's why, so it is proportional to, that is number of stimulated absorption of radiation is proportional to N1 rho V. So this is equals to N1 B12 rho V. So B12 is nothing but Einstein's coefficient. So now by giving instant photon, this lower energy atom get excited and now it is in the higher energy state. So when it went to higher energy state, when it transits to higher energy state, then it emits, the emitting process takes place in two ways. One is spontaneous emission of radiation, another one is stimulated emission of radiation. So spontaneous emission of radiation. So in this type of emission, the excited atom in the higher energy level E2 can stay up to 10 power minus 8 seconds. This is a average time up to which an excited atom can stay at E2 is known as a lifetime of the excited atom. So the lifetime of an atom in the excited state is 10 power minus 8 seconds. The lifetime of an atom in the higher energy state is 10 power minus 8 seconds. After that, the atom transits to lower energy level. Okay, so here the excited atom in the higher energy level E2 can stay up to 10 power minus 8 seconds. After this 10 power 8 second, which is the lifetime of an atom in the higher energy state, if it is completed that 10 power minus 8 seconds at the excited state, it transits to lower energy level even by itself emitting a photon of energy. So after the lifetime of the excited atom in the E2, it transits to the lower energy level E1. So there is no other initiation, no energies takes place, or no energy we are going to give, or no photon is interacting with the atom. So here this is E1 and this is E2. So after a stimulated absorption of radiation, the atom is at the higher energy state. So now this atom will be here up to 10 power minus 8 seconds. This atom will be at the higher energy state 10 power minus 8 seconds. After this 10 power minus 8 seconds, this atom spontaneously comes to ground state, transits to ground state. Transits to ground state. Emitting photon of energy. So it doesn't transits normally to lower energy state, but it emits some photon of energy. So that energy E is equals to E2 minus E1. H nu is equals to E2 minus E1. That is E is equals to H nu. So that's why H nu is equal to E2 minus E1. Then nu is equals to E2 minus E1 by H. So this process where emission of radiation takes place by the transition of an excited atom by itself to lower energy level is known as spontaneous emission of radiation. So here in this diagram, after stimulated absorption of radiation, the atom is at the excited state, higher energy state E2. After the lifetime, 10 power minus 8 second, this atom itself transits to lower energy state by emitting photon of energy, H. Okay, so this process is called the spontaneous emission of radiation. So in this spontaneous emission of radiation, the number of spontaneous emission of radiation depends upon the number of atoms per unit volume in E2. So that is it. So no other dependence here, because in stimulated emission, if the incident photon interacts the lower energy state atom, then only this lower energy state atom gets stimulated and transits to the higher energy state. So if the atom in the lower energy state wanted to get excited, we need incident photon. So that it depends upon the instant radiation density and also the number of atoms in the lower energy state. So but here in the spontaneous emission of radiation, the atom which is at the higher energy state, if it finished the lifetime, then the atom itself comes to the lower energy state. So no energy is supplying here, no incident photon is interacting with the atom in the higher energy state atom. So the number of spontaneous emission of radiation depends upon the number of atoms per unit volume in N2. That is, it is proportional to N2. It is equals to N2A21. This A21 is nothing but Einstein's coefficient of spontaneous emission of radiation. Coming to a stimulated emission of radiation, the excited atom after being stimulated by the incident photon transits to a lower energy level even in a time less than the lifetime 10 power minus 8 second of an excited atom. So in the previous process, spontaneous emission of radiation, after the lifetime of an atom in the higher energy level, the atom transits to lower energy state by emitting photon. So in this second process, the atom is at higher energy state E2. Okay. So the excited atom after being stimulated by the incident photon transits to lower energy level even in a time less than the lifetime of an excited atom. So before the lifetime of an atom in the higher energy state, this atom get stimulated and transits to the lower energy state, okay, by emitting photons of radiation. So this transition emits photons of energy nu, that is E is equals to E2 minus E1, HU is equals to E2 minus E1, nu is equal to E2 minus E1 by H. H is nothing but Planck's constant, nu is the frequency and E1, E2 are the energy levels. So this process where the excited atom after getting stimulated by the incident photon transits to lower energy level by emitting photon is known as stimulated emission of radiation. So in this process, while the atom transits to lower energy level from the higher energy level, it emits incident photon and also the incident photon and also the emitted photon. So here the stimulated emission of radiation, what happening here, the photon is interacting with the atom, with the atom at E2 level, so that before the lifetime the atom, the incident photon interacting with the atom before the lifetime of an atom, that is 10 power minus 8 seconds, before 10 power minus 8 seconds the atom transits to lower energy state. So the lifetime is not completed of this atom, lifetime of 10 power minus 8 second is not completed yet now. And in the in meanwhile, what happening, the photon is interacting with this. So before the lifetime of an atom, it gets stimulated by the incident photon and transits to lower energy state by emitting photons of energy which have the same direction. So in incident photon and also initial energy also be emitted in this way. So stimulated emission of radiation. So the number of stimulated emission of radiation depends upon the number of atoms in the higher energy level E2 and N2, the incident radiation density rho V. So number of stimulated emissions is proportional to N2 and also proportional to rho V, because before the lifetime of an atom in the higher energy state, it is getting interacted with the incident photon, so that N2 it is proportional to N2, that is stimulated emission is proportional to N2 and also proportional to rho V. So it is also proportional to N2 rho V. So it is equal to N2 B21 rho V. So B21 is known as Einstein's coefficient of stimulated emission of radiation. Okay, so this is the processes happening when the atom get excited to the higher energy level. So in this process, in addition to emitted photons, there will be incident photons. All these photons have same energy and same frequency and are in phase. So as they reinforce together, it results high intensity, monochromatic, coherent radiation, that is laser radiation. So these are the three processes, that is stimulated absorption of radiation. So this is the atom which gets stimulated, which can stimulates to transit higher energy state. After transits to the higher energy state, it comes to the ground state by the two processes, which are spontaneous emission of radiation and then stimulated emission of radiation. So in the spontaneous emission of radiation, so after the lifetime of an atom in the higher energy state, the atom itself comes to the lower energy state by emitting some radiation, by emitting the photon. So this is spontaneous emission of radiation. So in the second type of emission, stimulated emission of radiation. So the atom is at the higher energy state And before the lifetime of an atom in the higher energy state, that is before the 10 power minus 8 seconds, the atom stimulated by incident photon, so it gains some energy from the photon and then transits to the lower energy state by emitting incident photon and also the photon, emitted photon. So that in addition to the emitted photons, there will be instant photon in this stimulated emission of stimulated emission of radiation. Okay, so because of all these photons have same energy and same frequency and are in phase, so that we are getting high intensity monochromatic coherent radiation, that is laser radiation. So in the next class we are going to talk about the differences between the spontaneous emission of radiation and the stimulated emission of radiation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.